Welcome everyone. This is lecture number 9. Today we're going to show you architectures that you can use for image classification. We'll introduce you to the concept of transfer learning and look at famous network for object detection. The course is already, has already progressed into the deep learning section. There are 4 more lectures coming up in the supervised field, subfield, and 2 more in the unsupervised section. Let's start by, introducing a wide-angle view of this field. You as an engineer that is supposed to build neural networks for a wide variety of tasks, you should be aware of problems and challenges in your data. You should be aware of stuff that relates to the different options that you have for the design or designing the architecture of your network. And also, once that model is set up, you should also be aware of details about how to actually train this thing. And while we should probably stress more and more the importance of the database, we will not look into that too much today. And also the learning algorithm, that has influence or that will affect the question whether your model converges or not, and how fast it learns and how well it actually performs in the end. We will not cover this. There are a lot of lectures you can find online and even in the stuff that we published before. And so today we're going to look at architectural design choices. We have already learned about convolutional layers. So, for example, the size of those convolutional kernels and the number of features per layer. You want to learn that all these choices will affect what kind of performance you will get in the end. That also obviously affects the number of parameters, which is a rough estimate about how powerful the model actually is and what kind of problems it can learn. Convolutional layers, for example, also introduce a so-called inductive bias, so it cannot, learn wide range dependencies. Correlations will have to be, limited in a small local spatial neighborhood. And so there are also other things that we haven't yet talked about and we will not talk about today. Terms like regularization are very important parts in designing the architecture and the learning process of a neural network, and you should be aware of these. Today we'll focus for 2 different tasks, image classification and object detection, on architectural options that you have, publications that you can find online that we'll summarize here for you so you kind of know what we'll be talking about when someone says VGG or YOLO. So today, as I said, we'll be first looking at image models, image classification models. So, you have an input image and the output is a list of class probabilities. So, whatever is visible in the image can then be represented in this kind of probability distribution. If you really want to know more about where, for example, that object is, you call that task object detection, and that's the second half of this lecture. So we already talked about how to represent the location in spatial dimensions of object in an image, and the most simple version or variant of that is using bounding boxes, and the parameters of those bounding boxes are then or will then be predicted by our network such that we have an idea of where those objects are in the image. And looking at the pixel level and the pixels membership to object classes, you can do that without like clustering them into those boxes. Then we call this segmentation, instance or scene segmentation, but we'll look at that in the next lecture. So in terms of architectural, improvements in the history of neural networks, now the most obvious development was that models became deeper and deeper. And so looking at 2012 and AlexNet as the model that won the ImageNet competition in that year, that had only 8 layers. And over the years, that number of layers skyrocketed to, in 2015, a whopping 152, although ResNet comes also in like shallower variants. Yeah. So the error rate continuously dropped, and it's now for ImageNet at a level where we have reached human accuracy. So for image classification models, there's a huge variety of design choices that you can take and hyperparameters that describe those design choices and those components. But boiling it down to the basics, what we always have is, given that input, a sequence of conv layers that obviously have to be configured in the size of the space that they cover and also the depth in terms of the features that they provide. Then we'll have pooling layers, so reducing dimensionality by either max pooling or average pooling on those things. We will have skip connections, not visible in this figure here, but we'll talk about what these are. And in the end, of that conv stack, let's say, or conv pool stack, we have a small network, maybe 3 or so fully connected layers that kind of have to classify the image representation that we have at the end of the stack here to the whatever output that we are training it to. You will see normalization layers like batch norm, or like you will see different sets of activation functions. But in the end, that is your prototypical image classification network. And that isn't even a new idea or a new structure. In 1989, Jan LeCun published a ConvNet architecture that they used to recognize handwritten digits. And so basically, that's the same structure, the same architectural sequence of operations that we saw in the previous slide. It had a number of 60,000 parameters, so it's a pretty small network. But I mean, those inputs were like 32 by 32 pixel digits, so that's for that time already something. And
23 years later, AlexNet was proposed by Alex Krzyzewski and also two famous people, Ilya Sutskever and Jeffrey Hinton. In 2012, AlexNet won, but looked pretty much the same as LeNet, the one that we saw before. It came with convolutional and max pooling layers. In the end, we had only 8 layers, but 60 million parameters, so a 1,000-fold increase in what we had in LeNet. And ImageNet is a much harder problem than MNIST, and therefore it's already clear that we need a little more power to increase the performance. But also AlexNet did a couple of small things differently. For example, it used ReLU, so rectified linear units, as activation functions instead of sigmoids. It used dropout to regularize and prevent overfitting, and I think they used heavy data augmentation, so brightness changes, rotations, and all these things to increase the number of samples that you have, but also show the network different versions of the same thing. Well, and that helped, and that was basically the start of deep learning. So 2 years later, in 2014, the network that won the ImageNet challenge was not VGG, but it's still here on my slides because it's still in use, because it's pretty simple, and it was placed second, and I'll show you the winner in 2014. But here the idea was, okay, making a network deeper and throwing more parameters at the problem worked before, let's try that again. And VGG has, depending on the version, 11 to 19 layers, and has up to, I think, 144 million parameters, and it works. It was placed second and is still in use for various applications. I'll show you in the second part of the lecture what I mean. And as a little twist in the story arc, the actual winner in 2014 was Inception, made by Google, or sometimes people call it GoogleNet, or GoogleNet. And so this thing was very deep, but only had 7 million parameters, which goes back to the design of these Inception modules. I'm not going to talk about that and how they solved that, but you see, people started to think, okay, maybe depth and maybe the number of parameters is in the entire and the whole story. So, only 1 year later, that that paper, Hey et al. In 2016 was published, and it asked a pretty intuitive or like logical question. So can we get better networks by just stacking more and more layers, and going deeper and deeper, adding more and more parameters? And theoretically or like intuitively, those deep networks should be at least as good as shallow networks, because if we trained a good network that is shallow and then compare it to a deep network, the training process could, let's say, find the same parameters for the first part of this network and then add identity mapping so that the input-output mapping stays the same. So there is a solution that the optimizer should be able to find. The thing is, it doesn't, and this was confirmed empirically through experiments. And so comparing a 20-layer network to a 56-layer network showed there is always a gap in training and also in validation. And so obviously the network cannot find this identity mapping. And the question is, okay, how do we find a good solution? How do we converge to a better network if we use more parameters? In 2015, the winner of ImageNet was ResNet. And ResNet's idea here was that if the optimizer, the learning process, can't find identity mappings, well then why not per default use them and let the networks or those layers only learn deviations from identity mappings. So that motivated these so-called res blocks, residual blocks, that are shown here. In input is fed into normal conventional batch norm and conv layers, but also are added onto this output. So what we actually have is like a shortcut that basically means the network or those layers have to learn a deviation from the identity mapping. Yeah? And that very simple idea now led to very deep networks that actually learn something, right? So if previously we stacked many layers, we would not get better, or get better only very slowly. And we will talk about that in the Q&A session, why you think that is. And those shortcuts enabled us now to learning very deep networks. By the way, and you'll see that later in, I don't even know if we have that coming up, recurrent networks and LSTMs. That's an idea that is, something that has been applied to other types of networks already. And these networks, those residual connections, help in distributing graded information, from the very first entry point in the graph down to the first layers. So that may also be like an explanation for you that you can intuitively get. And those residual connections, those so-called skip connections, now show up in many other networks from that time on. So ResNext, kind of a successor to ResNet, also uses skip connections, where the output or the input is added to an output of a block. And also DensNet, a very popular image classification network, uses those skip connections. So for example, here the output or the feature maps of early layers, so those are like low level features, let's say, are added to the output of later layers, which then helps later layers to also use these low level informations to finally classify an image. So now that you know some basic architectures, we should train you to be able to then train those models on some toy problems. And we'll now have a look at some data sets that we'll be using in your assignments. And then later, when you have become a machine learning engineer, when you're then tasked with solving real world problems, you may face the situation that there is no data set, or there's only little data available for you. So the following slides cover a method that's called transfer learning that will help you, alleviate this problem. The first data set we'll be working with is called MNIST. It's, it consists of those handwritten digits, so 0 to 9, and so it's a classification problem with 10 classes, and it's considered, solved already. So the error rate here, I think, is below 1% or so. But MNIST, I think, is always the go-to data set when you start developing new models. The next data set then is so-called the Fashion MNIST set, which was published by Zalando Research. It consists of those tiny 28 pixels by 28 pixels, pictures of t-shirts and shirts and pants and shoes. We again have 10 classes in 60,000 or 70,000 or so samples. So that is considered like plug and play replacement of MNIST, and you will be working on that too. You have seen instance and scene segmentation tasks in those GIFs before, and you will be working with a data set that's called cityscapes, which is, I think, already quite large to be working with as a student, but I think it's on the border, so I think you still should be able to actually train a model on this set. And here, that's again ImageNet with the 1,000 different classes. So this set has 14 million images. I think we are at the limit of what student computers can do, even really modern ones. But some of you may be able to actually train a model on these because they have strong GPUs at home. So that brings me to the topic of how long does training one of these models on one of these data sets actually take. And to give you like a ballpark measure, if you want to train a ResNet, just like the one that we discussed, on ImageNet, and you have 4 GPUs, like those GTX 1080, it'll take 3 days. Yeah, and so it's not something that you push a button and then you go have a coffee and then everything is done. No, it really takes time and energy, right? So the energy consumption for the training procedure on modern models is significant. And obviously the training duration depends on many architectural choices, design choices, the learning algorithm, and the stuff that we just discussed. And that also means that optimizing these hyperparameters requires you to train a model over and over again for different settings for these hyperparameters, right? So you don't have to do this manually. I mean, we all could, but there are hyperparameter optimization frameworks that we can use. So you give it your model and your hyperparameters that it should be optimizing, and then you leave it running for weeks and months sometimes. So that means that deep learning is time-consuming, is energy-consuming, and given a new problem, creates a big challenge for you. So do we have that kind of data already, or do we have to find experts and get labels for the data that we can record? Or how can we limit the number of parameters of the model so we don't need as much training data? And for some problems that's not even possible because there's no data available, or it's really hard to get data. Think of like X-ray or MRI images. That needs patience, and sometimes you just have a couple of those available, but you would probably need hundreds or thousands or even tens or hundreds of thousands. So that's in a magnitude, an order of magnitude that is unreachable for you. So what can we do? Let's say off-the-shelf solution for these kinds of problems is transfer learning. So that basically has 3 steps. One is you go to a website and download a pre-trained model. For example, VGG, like we discussed, that big 130 million parameter big ConvNet, and that is pre-trained on ImageNet. So it has seen many millions of images and has already learned those features that are relevant to classify those images into the 1,000 categories that exist in ImageNet. Now, then you'll take this guy and you'll freeze most of the parameters, and you then in the 3rd step fine-tune only those last layers on your training data that you have, right? So if you don't have any training data, then you can't optimize those parameters, and you can just try to use features. So in that last conv layer, for example, or even in those fully connected layers, you will have vectors of activations that kind of are representations of the inputs, and you can use these to then predict whatever you want to predict, whether a brain scan has cancer or not, or an aneurysm or whatnot. And by having labeled training data, by then training only those last layers of the parameters that you have, simplifies that learning task, right? So the entire network doesn't have to be randomly initialized, and then the whole thing needs to find its optimum. We'll reuse all those features that the ConvNet extracts from the images, and then will only optimize the classifier, which is here the last couple layers. So I like to think of this process as something like that. So imagine you have your data in a vector space, and I'm going to visualize for you only the 2 dimensions x1 and x2. And so let's say you have, I don't know, images of dogs and images of cats. And in the original data space, it requires a powerful classifier that has a very adaptive kind of decision boundary to actually tell cats apart from dogs. But what you can do is you use your pre-trained VGG and you push in your sample, and you take a representation in one of those final layers, and these representations will hopefully magically work like that, such that the cats are all ordered on one side of the space and the dogs are all on the other side of the space, so that the classifier for which you have to now optimize the parameters for, that this classifier doesn't have to be as complex and adaptive and powerful as the one here. It, in the simplest case, just needs to be a linear classifier. Yeah. And transfer learning has been used in many domains, in computer vision, obviously in a very famous algorithm that's called fast RCNN, which is a object detection a network. And it kind of takes the representations of a deep CNN for certain image parts, and then these representations are then classified or regressed into bounding box coordinates. And in other domains like image captioning, so here the goal is, given an image, produce a description, like a textual description of what's to be seen on that image. We can use a pre-trained VGG or another convolutional network then to represent the content of the image and then feed an RNN, a recurrent neural network, with that representation of the image that is then able to produce a sentence, like for example a straw hat or something. Yeah. Okay, last few words with regards to image classification networks. We've seen that actually works to go deeper and deeper. We can scale up networks. We can just have them bigger and bigger, have more parameters, and they get better. However, you should be using skip connections. You should be using modern architectures. And that brings me to the point, there's always a better model. So just go on Google and find ImageNet results or image classification challenge results, and you will find a better model. Just read the paper and you will find solutions and tweaks that will make your results better. Now, that brings me to one of those important things that you should be aware of. We see like a convergent evolution kind of thing in different machine learning domains. So in reinforcement learning, in language processing, and even in computer vision, transformers or transformer models are used. And so that's like an architecture that we haven't yet talked about, but we will. And these have made it possible to surpass even the best ConvNets. However, that is only possible using huge databases. And so Google has an internal set of 300 million or 3 billion images that obviously haven't been hand annotated, but with that kind of data, you can train those big vision transformers, and you will get very, very nice results if you're able to actually either invest that kind of money in machines or that kind of time to actually converge to something worth that time. Okay, so that was the first half of the lecture. Please read all the links that we share with you in the description of the video. I will post soon the second part of that lecture on object detection algorithms. See you then. Ciao.